On October 29th, comet C/2024S1 Atlas will disappear behind the sun at precisely the moment Harvard astrophysicist Avi Loeb suggests this enormous, high-velocity interstellar object might execute a concealed maneuver that could trap it permanently within our solar system. The official explanation labels it a transient comet. However, the preliminary data challenges this simple narrative. A nucleus potentially 20 kilometers in diameter, with a mass exceeding 33 billion tons, all while exhibiting virtually no non-gravitational acceleration despite violent outgassing activity. If Loeb's hypothesis proves correct, we might be observing the first interstellar visitor to establish permanent residence in our cosmic neighborhood, and we'll have no means of monitoring what transpires during this critical moment. What secrets lie hidden during this solar blackout, and whose interpretation will triumph when Atlas resurfaces? October 29th marks an absolute boundary on our calendar. On this date, C/2024S1 Atlas enters a blinding zone directly behind the sun, severing access for every Earth-based telescope. The celestial mechanics are merciless. Earth, Sun, and Comet align in perfect conjunction, with our planet positioned on the wrong side of the glare. For approximately 6 weeks, the most massive interstellar object ever identified will travel through space completely unobserved, its trajectory and any modifications concealed from direct surveillance. This blackout represents far more than a scheduling challenge. It means the defining moments, perihelion, the closest solar approach, and any potential orbital adjustment will unfold entirely beyond our capacity to witness. The Earth-Sun distance measures roughly 150 million kilometers. At conjunction, Atlas passes just beyond this threshold at 1.36 astronomical units from our star. No ground-based observatory can isolate its faint signature from the solar inferno. Even space telescopes like Hubble and the James Webb Space Telescope must stand down, their safety protocols activated by the hazard of pointing instruments near the sun. The practical consequence: a data drought extending from late October through early December. Astrometric tracking, spectral analysis, even fundamental brightness measurements, all go silent. The sole prospect for observation rests with a limited number of solar probes and coronagraphs, instruments designed for studying solar weather phenomena rather than distant comets. Their sensitivity and imaging frequency barely register objects as dim as Atlas. For the astronomical community, the observation window slams shut precisely as the narrative reaches its climax. Every question about natural departure versus engineered capture, about cometary body versus technological artifact, remains suspended in this enforced silence. The countdown continues, and the moment of truth will play out where no human eye can watch. Avi Loeb's attention locked onto the target. The instant early photometric data arrived. The initial size estimate for C/2024S1 Atlas, 20 kilometers across, struck like a seismic shock. For perspective, 1I/Oumuamua measured less than a quarter kilometer. 2I/Borisov, the previous interstellar comet, extended perhaps 1 kilometer in width. Atlas, by comparison, dwarfs everything survey programs anticipated discovering first by an order of magnitude. The measurement wasn't speculative. It derived from the object's luminosity, adjusted for distance and solar phase angle, then modeled against established cometary albedo values. With an apparent magnitude well above 12 and no indication of a dense, optically thick coma artificially inflating the reading, the conclusion became inescapable. The nucleus must be genuinely massive. Loeb's skepticism emerged from statistical analysis. Survey population models predict that for every large interstellar visitor, thousands of smaller, dimmer ones should have already been detected. The Atlas survey, alongside Pan-STARRS and the Vera C. Rubin Observatory, scans the heavens nightly, calibrated to capture precisely these fast-moving sun-grazing objects. Yet the first 2 interstellar discoveries were diminutive. Then, without warning, a giant materializes. The probability, according to any population distribution model, strains credibility. If the size estimate holds, either the surveys have overlooked a vast population of smaller bodies, or something rare and inexplicable is occurring. This forms the foundation of Loeb's argument. A. 20-kilometer interstellar object appearing so soon after the first two discoveries violates the power law expectations that underpin contemporary survey science. The statistical warnings blared not because Atlas was bright, but because its sheer magnitude contradicted everything astronomers presumed they understood about what should exist out there. For Loeb, that single figure, 20 kilometers, became the first and most striking anomaly in an expanding catalog of mysteries. A mass of at least 33 billion tons now anchors C/2024 S1 Atlas in the astronomical record books. This figure, derived from dynamical modeling and the comet's sustained brightness, overshadows every confirmed interstellar visitor preceding it. Yet the contradiction begins here. Despite vigorous outgassing rates approaching 100 to 150 kilograms per second, dominated by carbon dioxide, there exists no measurable non-gravitational acceleration. In cometary science, this represents the classic rocket equation problem. Outgassing functions like natural thrusters, nudging the nucleus incrementally off its predicted trajectory. For typical comets, even modest activity leaves a distinctive signature in the astrometric record. A gradual drift, a subtle deviation from pure gravitational motion. But the Minor Planet Center's comprehensive dataset, encompassing over 4,000 positional measurements, reveals no such deviation for Atlas. The upper limit on its non-gravitational acceleration registers below 15 meters per day squared, so minimal that only a truly massive object could remain so unperturbed given its observed activity. The mathematics sharpen the contradiction. Consider the measured gas production, multiply by the outflow velocity, and divide by the estimated mass. The expected reactive acceleration should manifest clearly in the data unless the nucleus is not only large but exceptionally dense, or the outgassing is perfectly balanced in all directions, a near impossibility given the comet's rotation and solar heating patterns. Monte Carlo simulations explore every plausible combination of nucleus dimensions and density. For anything smaller than approximately 5 kilometers across, or less dense than 1,000 kilograms per cubic meter, the calculations fail. Outgassing should have deflected Atlas from its predicted track long ago. Only a massive, solid body satisfies both the photometric and dynamical evidence simultaneously. Alternative explanations, such as jets firing in perfect opposition, or a swarm of loosely bound fragments, require fine-tuned physics and improbable geometric configurations. The mainstream model struggles to reconcile these numbers without invoking statistical flukes or special circumstances. For Loeb and his colleagues, this isn't merely a curiosity, but an open invitation to deeper investigation. If the mass is genuine and the acceleration is absent, the door to non-natural scenarios remains ajar. Survey science operates on numbers, vast quantities of them. For every giant object like C/2024 S1 Atlas, population distribution models predict the sky should teem with thousands of smaller, fainter interstellar wanderers. The reasoning is straightforward. Smaller bodies vastly outnumber large ones in every known asteroid and comet reservoir. If the discovery pipeline functions properly, the first interstellar objects found should be the tiniest, the ones that outnumber giants by orders of magnitude. But the observational record tells a contradictory story. The Pan-STARRS survey, the Atlas Network, and now the Vera C. Rubin Observatory have scanned the celestial sphere for years, cataloging millions of detections. Their sensitivity has improved to where objects merely dozens of meters across, if moving rapidly enough, would leave traces. The first two interstellar discoveries, Oumuamua and Borisov, fit expectations perfectly. Both were small, faint, and right at the detection threshold. Then, without precedent, Atlas appears, 20 kilometers wide, at least 33 billion tons, blazing far above the detection limit. No accompanying swarm of smaller cousins, no gradual progression in size, just a statistical leap that defies explanation. Population modelers ran comprehensive simulations. If C/2024 S1 Atlas represents a typical member of the interstellar population, surveys should have identified hundreds, potentially thousands of lesser objects by now. Instead, the tally stands at 3. Analysts at Pan-STARRS and Rubin flagged this discrepancy in internal communications, warning that the probability of discovering a giant before its smaller relatives is astronomically remote. less than 1 in 10,000 by conservative estimates. The power law, the mathematical backbone of size distribution analysis, appears fractured. Either the universe conceals a vast population of faint, elusive bodies that have somehow evaded detection, or Atlas represents an outlier that defies every statistical expectation. For those monitoring anomalies, this isn't simply a curiosity. It's a signal that something fundamental in our understanding is incorrect, and that the story of C/2024-S1 Atlas is already rewriting established principles. Trajectory maps for C/2024-S1 Atlas reveal a path that hugs our solar system's ecliptic plane, tilted by merely 5 degrees. For an object arriving from interstellar space, this kind of alignment is profoundly unusual. Most known comets and asteroids, even those native to our system, follow orbits that tilt and twist through the solar neighborhood at various inclinations. A random visitor from beyond should slice through at a steep angle, its course shaped by the gravitational chaos of distant stellar systems. Instead, Atlas glides almost parallel to the planetary disk, threading a corridor typically reserved for indigenous bodies. The geometry becomes stranger upon detailed examination. In the weeks preceding perihelion, Atlas strings together a sequence of close encounters with major planets. On October 3rd, it sweeps within 29 million kilometers of Mars, a margin that, by interplanetary standards, qualifies as a near miss. The sequence continues. Later, its trajectory brings it within significant range of both Venus and Jupiter, accumulating a series of planetary flybys rarely observed outside meticulously planned space missions. Orbital dynamicists calculated the probabilities and discovered that the compounded odds of such a massive, fast-moving object threading this precise path are vanishingly small. For each planet, the probability of a close passage is low. 4-3 in succession, the likelihood plummets below 1 in 1,000, possibly much lower when accounting for the specific geometry and timing. This alignment transcends mere curiosity. The ecliptic hugging orbit positions Atlas optimally for gravitational perturbations. Each planetary flyby could theoretically adjust its velocity or bend its trajectory, but the genuine intrigue lies in how these stacked encounters establish the conditions for the perihelion moment. The trajectory appears fine-tuned, almost as if engineered to maximize options for a dramatic maneuver near the sun. For those examining the boundary between natural phenomenon and intentional design, the flight path itself becomes silent testimony, raising questions that numerical analysis alone cannot resolve. The first images of C/2024-S1 Atlas disturbed observatory teams worldwide. Instead of the anticipated tail structure, a concentrated forward luminosity dominated the sunward hemisphere, a brightness that resisted every correction for motion blur or instrumental artifacts. Imaging analysts at Gemini South and the Very Large Telescope scrutinized the data exhaustively, searching for technical explanations, but the asymmetry persisted. As the comet approached closer to the sun, this forward glow diminished and a conventional tail began extending away from the nucleus, aligning with solar wind direction. Some interpreted this as a geometric illusion. Others viewed it as evidence of genuine transformation, perhaps a crustal layer fracturing or a sudden eruption of activity from beneath the surface. Spectroscopists redirected their focus to the comet's chemistry. The James Webb Space Telescope's NIR-SPEC instrument, during a narrow observation window before solar conjunction, captured a volatile ratio that challenged expectations. Carbon dioxide outpaced water by nearly 8-1. For solar system comets, water vapor almost universally dominates as the primary volatile. This ratio suggested a nucleus either preserved in deep freeze, since its interstellar journey, or mantled in a layer of carbon dioxide frost. Calibration teams urged restraint, flagging the result as preliminary until additional data could confirm or refute the finding. Theories proliferated rapidly. Some researchers pointed to a carbon dioxide crust shielding a water-rich interior. Others raised possibilities of contamination or modeling errors. The debate spilled into late-night collaborative channels, with each team defending their interpretation against alternatives. Then in late September, a sudden surge of green emissions swept through the coma. Both amateur and professional astronomers reported the chromatic shift, attributing it to C2 or CN molecules fluorescing under intense solar ultraviolet radiation. For most comets, green coloration appears near perihelion as volatile ice's sublimate, but here it arrived early and intensely, exceeding model predictions. The color change raised fresh questions about the stratification of volatile ices and the comet's surface chemistry. Each anomaly, optical, chemical, chromatic, layered uncertainty upon uncertainty. With the comet slipping behind the sun, answers would have to wait, leaving its true nature suspended between natural artifact and something far more provocative. Avi Loeb's hypothesis centers on a temporal window, so brief it barely registers on cosmic timescales. At perihelion on October 29th, C/2024 S1 Atlas will be traveling at nearly 44 kilometers per second, an interstellar projectile arcing just 1.36 astronomical units from the Sun. For any object on a hyperbolic escape trajectory, this represents the singular moment where a single impulse, a velocity change at just a few kilometers per second, could tip the balance from permanent escape to solar system capture. The physics are unforgiving. To transition from an outbound interstellar trajectory into a gravitationally bound solar orbit, Atlas will require a delta V of approximately 8 kilometers per second delivered precisely at closest approach. Anything less, and the comet races onward into the void, never to return. Anything mistimed, and the opportunity vanishes. This maneuver, if it occurs, will be completely invisible. The sun's overwhelming glare blinds every telescope on Earth. Even the most sophisticated space-based coronagraphs will struggle to distinguish a faint, fast-moving speck against the solar corona. Detection limits of these instruments hover around apparent magnitude 8 to 10, far too insensitive for a comet like Atlas during solar conjunction. The practical effect. Any change in trajectory, any burst activity or propulsive thrust would slip past unnoticed until the comet reemerges weeks later. The Mars flyby on October 3rd, at just 29 million kilometers distance, offered brief hope for direct imaging. High-rise mission planners debated the possibility, running calculations on angular resolution and apparent brightness. The numbers closed the door definitively. At that distance, a 20-kilometer object subtends less than 0.15 arcseconds, smaller than HIRSE's diffraction limit. Even as a point source, Atlas would be too faint for detection. No surface features, no jet structures, no probe deployment observations. The most powerful camera orbiting Mars can only observe darkness. For Loeb and his supporters, this enforced invisibility is simultaneously a frustration and an opportunity. If a maneuver is attempted, the evidence will be inscribed in the comet's orbital elements, waiting to be deciphered when Atlas steps back into visibility. Tom Statler, NASA's lead planetary defense officer and small-body scientist, draws an unambiguous line. It looks like a comet. It behaves like a comet. It very strongly resembles in virtually every measurable way the comets we study for decades. That's the baseline position. The mainstream perspective holds that C/2024 S1 Atlas fits, albeit awkwardly, within a broad and unruly family of natural comets. Unusual mass, statistical anomaly, odd chemistry. Comets are inherently messy, preserving diverse formation conditions, trajectory quirks and planetary flybys, coincidence multiplied by the immensity of space. Astronomers like Karamich and Kyunki echo this stance, pointing to selection bias, incomplete survey history, and the fundamentally unpredictable behavior of volatile-rich bodies. For them, the burden of proof lies squarely with extraordinary claims. Loeb approaches the identical dataset from the opposite philosophical direction. He doesn't employ a formal probability scale, but his argument accumulates anomalies: mass, size, ecliptic alignment, planetary encounters, chemistry, optical behavior. The more these features cluster in a single object, the stronger the case becomes for heightened scrutiny. In Loeb's framework, when sufficient oddities accumulate, the only scientifically responsible action is to maximize observational resources, especially when a rare event like perihelion behind the sun could conceal a defining maneuver. He never assigns numerical probabilities, but the principle is straightforward. If the catalog of outliers grows sufficiently long, treat the object as if the stakes are significant. This doesn't require believing in artificial origin. It requires responding proportionally to accumulated uncertainty. The next critical observation window opens in early December when Atlas reemerges from solar conjunction. Every major observatory will be prepared to check for changes in orbital parameters, rotation state, and spectral signatures. By March 2026, as Atlas approaches Jupiter for a final gravitational interaction, a second comprehensive dataset will test whether its trajectory remains hyperbolic or if something fundamental has changed. The decision framework isn't about scoring anomalies on a subjective scale. It's about tracking concrete, falsifiable predictions. If the orbit maintains its expected course, the natural comet model holds. If it doesn't, if the orbital elements reveal capture or unexplained trajectory modification, the debate will enter an entirely new phase with profound implications. For now, the only certainty is that the story depends entirely on what the data reveal when the blackout ends. On October 29, 2025, C/2024's 1 Atlas will pass behind the Sun, severing all Earth-based observation at the precise moment Avi Loeb theorizes a retrograde orbit capture maneuver could anchor it permanently within our solar system. The object's estimated 20-kilometer diameter and mass exceeding 33 billion tons, combined with negligible non-gravitational acceleration and a carbon dioxide-to-water ratio approaching 8:1, collectively challenge expectations for a natural interstellar comet. Yet as of today, no direct evidence confirms any artificial origin or intentional behavior. NASA's official position maintains that comets can exhibit unpredictable characteristics, and numerous questions, such as the origin of its green spectral phase and the ultimate nature of its trajectory, remain unresolved through natural explanations alone. When Atlas emerges from behind the Sun in December, its updated orbital elements and chemical signatures will provide the conclusive test. Orbital mechanics don't lie. If the comet's trajectory has shifted from hyperbolic to elliptical, if its velocity has changed in ways unexplainable by gravitational interactions alone, the implications will be inescapable. If it continues on its predicted escape trajectory, the natural interpretation prevails, and Atlas will fade into interstellar space as mysteriously as it arrived. Until then, the only certainty is the imperative for rigorous observation and open scientific discourse. The universe rarely offers such clear experimental tests. Whatever Atlas proves to be, comet or something more, the answer will be written in the mathematics of its motion, waiting to be read by those patient enough to watch the darkness and calculate what emerges from behind the Sun. The clock is counting down. October 29th approaches, and for 6 weeks, humanity will be blind to one of the most significant astronomical events in modern history, left to wonder what is happening in the light we cannot see. The first detection came from the Gemini South Observatory at 3:47 Universal Time Coordinated, a faint point of light, exactly where the orbital predictions said Atlas should be if it had continued on its natural path. Within hours, observatories across 3 continents confirmed the sighting. The comet had survived perihelion, but the crucial question remained unanswered. Had anything changed? Dr. Sarah Chun at the Minor Planet Center began the painstaking process of computing the new orbital elements. Each additional positional measurement refined the calculation, narrowing the uncertainty. By December 10th, she had enough data to run the preliminary analysis. Her hands trembled as she reviewed the output. The orbital eccentricity, the parameter that determines whether an object is bound to the Sun or escaping into interstellar space, read 1.00847, a hyperbolic orbit. Still, Atlas was leaving, just as the natural comet model predicted. Relief swept through NASA's Planetary Defense Coordination Office. Tom Statler prepared a statement affirming the comet's natural origin. But something nagged at Chun. The number was too perfect, too close to the boundary between capture and escape. She ran the calculation again with different parameter sets, adjusting for solar radiation pressure, relativistic effects, every subtle force that could influence the trajectory. The eccentricity value shifted slightly with each iteration: 1.00834, 1.00851, 1.00829. Then she noticed something that made her blood run cold. Avi, you need to see this. Chen's video call caught Loeb in his Harvard office at 2 a.m. He'd been expecting her call. The orbit? He asked simply. It's hyperbolic, but barely. We're talking about an eccentricity that puts Atlas within 0.3% of being captured. Avi, the probability of a random interstellar object passing this close to the capture threshold is... She pulled up her statistical analysis. 1 in 12,000. Loeb leaned forward. What's the uncertainty in your measurement? That's the problem. Our uncertainty range is plus or minus 0.0012, which means we can't definitively say whether it's escaping or captured. We need more time, more observations. How much time? 3 weeks, maybe 4. By January, we'll know for certain. But Loeb was already thinking ahead. Sarah, run a different analysis. Compare Atlas's current orbit to its predicted trajectory based on the October 3rd Mars flyby data. Tell me if there's any deviation that can't be explained by gravitational interactions alone. 12 hours later, Chen sent her results. The trajectory showed a velocity anomaly of 0.8 kilometers per second. Small, but statistically significant at the 3 sigma level. Something had changed Atlas's course during the solar conjunction. The question was, what? Dr. Marcus Webb wasn't looking for comets. As a solar physicist analyzing SOHO coronagraph data, his focus was on coronal mass ejections and solar wind structures. But when he processed a backlog of images from late October, something extraordinary appeared in the frames from October 29th. 12:14 Universal Time Coordinated to 12:31 Universal Time Coordinated. A 17-minute sequence that had been flagged as corrupted data and initially discarded. Webb recovered the files and enhanced them. There, barely visible against the solar corona, was Atlas, but it wasn't alone. For 42 seconds, the comet's brightness increased by a factor of 6, not gradually like outgassing, but in a sharp spike. Then, even more remarkably, a directional jet appeared from the nucleus's sunward side, a concentrated beam lasting exactly 8.3 seconds before cutting off as cleanly as it had begun. Webb ran every analysis he knew. Solar interference? No, the timing was wrong. Instrumental artifact? Impossible. The pattern showed up across multiple wavelength filters. A natural outburst? Perhaps, but the geometric precision was unprecedented. The jet axis aligned to within 0.4 degrees of the optimal vector for orbital capture. He calculated the thrust required to produce the observed change, approximately 2.1 times 10 to the power of 13 newtons over 8.3 seconds. The delta V matched Chen's velocity anomaly almost perfectly. Webb stared at his screen for a full minute before reaching for his phone. His call wasn't to NASA. It was to Avi Loeb. The leaked SOHO images hit AR-14 at 6 a.m. Eastern Time on December 18th. By noon, the paper had been downloaded 40,000 times. By evening, it was the lead story on every major news outlet. NASA convened an emergency press conference. Tom Statler faced a room packed with journalists demanding answers. The SOHO observations show an outgassing event consistent with a fragmentation or crust breach scenario. We've seen similar behaviors in other comets approaching perihelion. While the timing and directionality are unusual, they fall within the range of natural cometary activity. A reporter from Scientific American stood. Dr. Statler, the jet occurred at the exact moment and in the exact direction needed to begin orbital capture. What's the probability of that happening by chance? Statler's jaw tightened. Cometary jets are influenced by rotation, solar heating patterns, and subsurface structure. Without detailed knowledge of Atlas's internal composition, we can't calculate meaningful probabilities. But you're not ruling out the possibility of something artificial? I'm saying we need more data before drawing any conclusions. Meanwhile, Loeb was giving his own interviews. He was careful, measured. He'd learned from past controversies. What we're observing is a sequence of anomalies that, taken individually, might be explained naturally. But when you examine the totality, the size, the trajectory, the timing, the jet characteristics, you're forced to ask whether we're witnessing something unprecedented. Science advances by following the data, even when it leads to uncomfortable places. Sarah Chun hadn't slept properly in 3 days. The latest astrometric data from the Vera Rubin Observatory had just arrived, the most precise measurements yet. She ran the orbital determination one final time, incorporating every observation from December and early January. The calculation converged. The eccentricity value stabilized. 0.99973. Atlas was captured. Not by much. It would take 127 years to complete its first orbit around the Sun, swinging out to 89 astronomical units at aphelion. But it was bound. An interstellar visitor had become a permanent resident of our solar system. Chun cross-checked her work obsessively. She had 2 colleagues independently verify the calculation. All 3 arrived at the same conclusion. The statistical significance was overwhelming. 5.2 sigma. In particle physics, that's the threshold for claiming a discovery. She wrote up her findings in a terse, 4-page paper. No speculation, just mathematics. The title, Orbital Evolution of C/2024S1, Atlas Transition to a Bound Solar System Orbit. Before submitting it to Nature, she sent a preview copy to Loeb. His response arrived within minutes. Sarah, you've just changed history. Whatever Atlas is, it's here to stay. And now humanity has 127 years to find out the truth. 6 months later, NASA Administrator Bill Nelson stood at a podium in Washington, D.C., flanked by representatives from ESA, JAXA, and the Chinese National Space Administration. The announcement had been telegraphed for weeks, but it still sent shockwaves through the scientific community. Project Envoy would be a joint international mission to rendezvous with C/2024S1 Atlas during its outbound journey. Launch window, November 2027. Transit time, for years. The spacecraft would carry a comprehensive instrument suite, high-resolution cameras, ground-penetrating radar, mass spectrometers, and sample return capabilities. The mission objectives were straightforward. Determine the comet's composition, internal structure, and, most critically, whether the October 29 jet event was natural or artificial. Loeb was named to the mission scientific advisory board, alongside Karamich, Quanji, and a dozen other planetary scientists. The first planning meeting was cordial but tense. The natural versus artificial debate hadn't been resolved. It had merely been postponed until they could examine Atlas up close. Whatever we find, Meach said during the closing session, we're going to have to live with the answer. Loeb nodded slowly. The universe has given us an extraordinary gift, a mystery we can actually solve, not with speculation or probability arguments, but with direct observation. That's what science is supposed to be. As Atlas recedes into the outer solar system at 31 kilometers per second, it carries humanity's questions with it. Is it a comet that happened to undergo a perfectly timed outburst during solar conjunction, a coincidence of geometry, chemistry, and timing that occurs once in hundreds of thousands of years? Or is it something more deliberate, an interstellar probe executing a capture maneuver that played out exactly as designed, hidden from view until the evidence could no longer be erased? The SOHO data remains ambiguous. The jet's precision argues for artificiality. Its spectroscopic signature matches natural cometary outgassing. The trajectory change is significant but not impossible through natural means. The size, mass, and chemistry all push against statistical expectations without quite breaking them. In laboratories across the world, researchers are developing new analytical techniques for Project Envoy. In 2031, when the spacecraft reaches Atlas, every sensor will be focused on answering a single question. Are we alone? Until then, Atlas hangs in Earth's night sky. Faint now, requiring telescopes to see, but undeniably present. A visitor that chose to stay. A mystery that refused to leave. And every clear night, Avi Loeb stands at his telescope, watching that faint point of light and remembering the October morning when a graduate student first showed him the unusual photometry of a newly discovered comet. He'd said then that the universe doesn't care about our preconceptions. It shows us what it shows us. Now it has shown us Atlas. And in 4 years, humanity will finally reach out and touch it. The answer is coming, whether we're ready for it or not.